Hello everyone, my name is Thabang Kgarume. I'll be presenting a project on the technologies to identify geological structures on the face, such as ground penetrating radar and thermography. This was one of the work packages of the SAMEDI's Advanced Ore Body Knowledge. Here, when we look at the need, we see that we need a better understanding of our underground excavation in terms of its stability. This is very necessary because we encounter fractures, joints, faults, which can compromise the stability of the excavation. We propose a solution using non-destructive method. Non-destructive meaning we will not be doing any physical destruction of the rock, but rather we'll be using technology. We will be sending radio waves inside the rock mass and receiving the energy coming back to be recorded. We propose ground penetrating radar coupled with thermography in order for us to get a better understanding of the stability of the rock mass and to map the structures within the hanging wall and the general surrounding rock mass. We can see that most of the common causes of fatalities shown on the figure, the prominent one still remains the falls of ground, but we can see that the industry has went a long way in achieving its zero harm objectives. Although the curve has plateaued, there is still some need for us to reduce the number of falls of ground in underground mines. So using these two technologies, we want to demonstrate the joint use of ground penetrating radar and thermal imagery in order to enable the excavation integrity and stability assessment. While the ground penetrating radar will be used to send radar waves into the rock and then recorded, thermography will be used to take pictures of the hanging wall using temperature differences to delineate loose blocks along the skin of the excavation. A Noggin 500 radar system from Sensor 7 software was used to collect the data in the underground environment. A 500 megahertz antenna was used for data collection, which achieves a depth of about 6 meters within the hanging wall. The technology basically sends out radio waves using a transmitter where the energy penetrates the rock, and whenever it encounters a discontinuity, which is caused by the changes in electrical properties of the rocks due to a fracture or maybe a fault, the material basically will have different electromagnetic properties and will reflect the energy back. This will be recorded in the receiver, and we will measure the travel time of the radar waves. Traditionally, these surveys are done in two-dimensional, but in our study, we expanded the study into 3 dimensions by creating a grid along the hanging wall and collecting many different GPR scans along the hanging wall. We also use infrared camera to take pictures, thermal images of the hanging wall. The idea here is that the thermal camera uses temperature differences along the rock mass to identify loose blocks. This happens because the rock mass is generally at a higher temperature than the surrounding air due to the ventilation. Because of the differences between the loose rock and the intact rock, heat is lost, and that can be used by the camera to delineate the position of the loose blocks along the hanging wall. This will be done at the same area where the GPR is done. 2 underground mines using the board and pillar method were used as test site. As one can see, the acquisition parameters at the bottom here, at both sides we used 500 megahertz antennas. Our line length were generally about 8 meters along the hanging wall. Our line spacing, we kept it at 0.2 of a meter so that we can create a close dense data of number of lines collected along the hanging wall. On the second mine, we actually did 3 blocks along the face, moving to the back area and around the pillar which surround our survey area. The idea there is to understand the behavior of the rock mass, not only from the face, but to move towards the back area and around the pillar. These results that I'm presenting are some of the results that we got from the 2D radar grams. On your left, you can see the radiogram as it is, and on the right included is the interpretation of the radiograms. We can see that there are, within a meter, there's a horizontal reflector and a dipping fracture, this is what we look out for. The interaction of these horizontal structures and the dipping fractures can actually create loose blocks along your hanging wall. We also identified a fault which was mapped on our mine plan. The radar was able to detect the fault. This scan was taken at 2.8 meters along the survey grid. On the same survey grid, we're showing another scans taken at 3.6 meters along the survey grid. This is at a distance of about 0.8 of a meter. But one thing to note here is the changing character of the radiogram. We can see that the fault in a space of 1 meter has extended way deeper into the hanging wall along with the fracture, which seems to be approaching towards the skin of the excavation. This is the value that 3D surveys bring, that when a 2D data is collected, just a couple of meters away from that, the picture could look different from the previous scan taken. This is showing the result of the radiogram that one can achieve when we look at the hanging wall around the pillar. We can see that also the character is different, although we still see that horizontal structure and a bit of some dipping structures, but we see that it's highly dominated by dipping fractures on the hanging wall of the pillar. This shows that this can be used to characterize the rock mass around your working area. We also took another scan at the mining phase, looking ahead of the mining phase. Then what the radiogram showed us is also the different character and the changing character of the radiogram. As one can notice, we were able to identify stress-induced phase parallel fractures. Here they were extending about 4 meters within the mining phase. So this also shows another value that GPR can give in understanding the fractures ahead of the mining phase. These are the scans taken along the pillar side wall. What they reveal is that we can see some complex fracturing within the pillar rock mass. This involves side wall parallel stress-induced fracturing, complex fracturing, and we see that we could potentially use this to provide an indication of the stability of the pillar in terms of the fracturing occurring within the rock mass. Just some further consideration, we can see that if we look at the left radiogram, we can see that the dipping fracture within 1 meter on the right radiogram is not visible. That is purely due to the color palette used to display your data. This is just for the operators to keep that in mind, that the displaying of data also acts as a filter on your data, especially for dipping reflectors. The temperature differences were delineated using the infrared camera, but what we notice is that you need large thermal gradient for the methodology to work. This basically means that this method will be more applicable to a freshly blasted phase. That is one of the pitfalls of this methodology, is that you really need a high temperature gradient. This would mean you really need stopes with higher temperatures, for example, in deep level gold mining and some of the platinum mines, as they have high temperatures underground. We started looking at the data in terms of our extracting data from our 3D grid. These are just showing the line positions of the different lines within the block. We can notice that we get more information because we can, extracting from the lines, we can follow different features to see their behavior across our survey grid. This is the advantage of volumetric data, that data can be extracted at different positions to see the character of your rock mass. And ultimately, one can come up with a 3D cube or a volume of the data sets. Another advantage is that one can extract 2D scans of the volume in any different desired direction to see the continuity of the structures. Here is what one can do, have interactive 3D GPR models of the hanging wall, again just to see the behavior of the hanging wall, how it's behaving, and the fractures within the rock mass. This is another block looking at the side of the pillar. We can now see the intense dipping fractures that we image within the hanging wall of the just on the side of the pillar. We can see that thermography is highly dependent on the large thermal gradient between the host rock and the ventilation air. So this makes this method to be more applicable in freshly blasted phase as the temperature of the rock mass is still high. Once the phase stays for longer and loses the temperature, the method becomes hard, struggles to detect the loose blocks along your rock mass. All this data demonstrated that the value of GPR in understanding the rock mass stability, and we understood the rock mass fracturing. They were successfully imaged, particularly dipping fractures, which could potentially form key blocks within the hanging wall. The acquisition of GPR data, particularly 2D scans, are very quick to achieve. They will take a minute to 2 minutes, for example, for a 10-meter line scan. However, when conducting 3D datasets, this will take a bit of a long time to achieve due to the marking of the desired grid along the hanging wall and the collection of the parallel 2D lines. To streamline this process, we suggest a multi-sensor GPR arrays that should be considered for data acquisition. For example, if one has a 4-channel multi-sensor array, this will fast-track the acquisition 4 times compared to a single antenna. For the way forward for the industry, 3D GPR should be the way forward in order for us to have a better understanding of the rock mass stability. We saw that it will not only fast-track the data acquisition, but it will also improve the inline accuracy and synchronization of the data. Furthermore, we need to mount the sensor array on a mobile platform, thus removing personnel from high-risk areas and from manually executing the scanning. This system should be able to perform advanced data processing of 3D datasets on board and visualize the data to the operator in real time. On-board processing should use techniques such as machine learning and artificial intelligence for automatic tracking of the continuous structures that we showed in a 3D cube. But this should be done on board by the GPR system, looking at how the technology has advanced, and they must be able to report to the operator. We will also looking at taking all these data sets and the models, and then we need to integrate them into the Mines 3D CAD softwares in order to give the operators a better picture of the surveys relative to their working areas. This will give more value into their survey data sets as it will be integrated with the mine processes. The research team would like to thank the Department of Science and Innovation, Minerals Council, and the Mandela Mining Precinct for their support on this project. Thank you.